what is the sum of the four? There is Archimede.
The added masses force.
What do you call him in Italy? Archimede.
Archimede.
Archimede force, okay, and the weight. So they are exactly opposed in fixed point. So these are the two external forces at fixed point, and they are opposed and equal to zero. When there is some wind, there's an external force adding, and then if you linearize the equation, eventually you get a system which is now controllable. So it's like a plane has this type of current, which is the gravity. If you have no gravity, and you work out the equations of a plane, you would see that a plane wouldn't be stabilizable at a fixed, when hovering, for example. And it is really because of gravity that when you linearize the equations, you get a controllable system. But, so this means that the external forces usually are different from zero for an airplane or for another aerial vehicle. But there are cases where you can imagine maneuvers when this force, external force, becomes equal to zero. For example, a plane that would fall down like this vertically at constant speed, when you have the drag directly opposed to the weight of the plane with no lift. So that you have a plane going down like this. This, in that case, for the external forces are equal to zero. Or if you have a vehicle and direct-rated vehicles, so with the thrust, and you can change the orientation, but you have no gravity, then again, at whatever point, then fixed velocity, you will have external forces equal to zero, and then you will fall upon the problem I'm explaining here. So this is why we have tried, we have worked out with Daniele, for example, a theory for controlling these planes, but which is based on classical theory, basically, of when the linearized system is controllable. But nowadays we're trying to go a bit further and work out another control using transverse functions, even in the case when the external forces are equal to zero. So here, this is just a preliminary simulation of a plane controlled with a transverse function. So we'll see it looks like a classical way of controlling the plane, actually. Nothing very different. Because here we are, these are good solutions. This is looping. On top you have the three planes, projections on the three planes of a motion. And in the end we stop. We assume this is a tail-theta plane, so you have enough power to keep it in flight to hover. So just to illustrate the way transverse functions, this approach can be used in quite many systems. Thank you for your attention, and I'll be happy to.
I have a question because and also a comment. I personally think that this is really related to what people is what's trying to do here, because the stabilization of an unfeasible trajectory is somehow also related to our manipulators, where we want to stabilize different tasks and we cannot stabilize them all, because we might have different tasks and there might not exist a configuration for the robot that satisfies all tasks. So probably I am thinking that this approach might be somehow also useful for stabilizing a stack of tasks when we have different tasks and these tasks are not always feasible. So I don't know what to think about it, and if you see an application for in this case.
It's too early to say. You'd have to explain to me your problem, or
okay.
I don't want to say just bullshit.
Yes. And also another question, then a question. So basically, you have ensured practical stability for unfeasible trajectories, right? But what about the feasible ones? So then the feasible ones, I think, that are asymptotically stabilizable, right?
Yes, we have results showing. In fact, for complicated systems, it's not simple to show that kind of results. But indeed, we have shown in some, for example, in case of cars, that how to modify the transverse function so that, or at least get the transverse function from a previous transverse function to ensure asymptotic stability along feasible trajectories on top of practical stability all the time.
Exactly.
So basically, the idea is that your transverse function should also be able to go through zero. Zero must belong to a transverse function, so that when you take x minus the transverse function, it would be x minus 0, so that if x minus the transverse function goes to 0,
yes,
then x goes to 0.
And then you get the convergence.
And then you get the convergence, asymptotic convergence, provided that you chose the parameters with the right sign, things like this, depending on the sign of the reference trajectory.
Okay.
So basically, you end up with the same properties that you have with classical feedbacks, with the same conditions. I'd say to obtain asymptotic stability in the case of feasible trajectories. But on top of that, you have practical stability with a uniform rate of convergence to the desired neighborhood, which is very important because other people have tried to show also asymptotic stability to improve asymptotic stability for very special trajectories, but there is always a culprit. They don't get uniform asymptotic stability, and in practice this is very bad.
Questions?
Yeah. So, are there any studies on how to choose the transfer function of your parameters so that you, for example, minimize a certain cost function while trying to track the reference trajectory?
Yeah, I mean, this is a very, we have thought a bit of it, and we don't know if we can solve that kind of questions. Because this is a compromise. I mean, it all is compromise. For example, I was showing you the question of a car. You see that if you want to follow closely a non-feasible trajectory, you have to make very, very high frequency maneuvers. That means you will consume a lot of energy. So you want to track closely, consume a lot of energy. You don't want to track closely. You of course gain. You won't spend as much energy. But then what can you do? What is a good compromise then? I would say it depends on the application, and it's difficult to be systematic. To have a systematic answer for that. Anyway, it would be whatever criterion that you choose would be a different, difficult answer.
And the last question, yeah. Okay, sorry.
Yes, you ask that.
Yeah.
No.
If you have a non-smooth system, do you think the same method can work?
What do you mean by non-smooth system?
For instance, a differential equation which has discontinuous inputs which are externally, like disturbance.
Well, in physics, I mean, it's always a reason between physicians. I mean, does the physical world is continuous or discontinuous first? I mean, I don't know. I mean, depends on the scale on which you're working. I mean, if you think of finger, it is not discontinuous because you have some compliance, and usually on a robot you will use some compliance. If you don't, you will be in trouble most of the time because you will have chattering, some type of bad effects. So compliance is good. So it implies also continuity. So for physical systems, non-discontinuous systems are not very physical to me. But, and on top of that, the problem with discontinuous inputs makes the problem also difficult to solve, I mean, to define theoretically what the trajectory is. You have to define different use, but especially when you are discontinuous around a point where that you want to stabilize. So you imagine like a step response like that, or a sign, x dot equal u equal minus sine of x. Okay? It turns out in that case, in the sense of Philippov, you have to define what is the solution to that kind of system around 0 at 0. And this can be done only in a mathematical sense, not in a physical one, because in the physical one you cannot reproduce this system. So you have to define first a mathematical sense for which you don't even know if it is physical, or if in physical case it would be a good sense. So it turns out for the specific case it is indeed a stabilizing feedback, but for example in the case of a mobile robot, a unicycle, if you use the optimal control, even bounds on the inputs, it turns out that the optimal control, which is discontinuous, is not stabilizing in the sense of Philippov I was telling you before. So I don't know if I answered your question. This is why we work with, we try to work with differentiable inputs, like people do with linear systems. There is a reason why people with linear systems, why you were taught linear control for linear systems. It's not only because it's simpler, it's also because it works in practice better than the discontinuous control that we give you shattering and things like this.
Yes, the last question I have: how can I find the transfer function for a given system?
Just
So the proof
for
is
example,
constructed.
work
right?
out the control vector.